Anyway, we're going to start off with Brian LaCour, one of the very few three-timers at these workshops. This is the third year we've done it. You've been gracious enough to come every year and always does an awesome job. He's from UT Austin and all of those things.
Yeah.
But he's going to talk about the exploring quantum optics with the Virtual Quantum Optics Lab, which is a great tool.
All right. Thank you very much, Justin. It's always a pleasure to come to this workshop. I really enjoy it, and I enjoy interacting with everybody here and seeing a lot of old and new faces. So it's really fun. I don't recall exactly how Justin first came upon me, but I remember getting a call from him from out of the blue. It's like, hey, I'm doing this workshop. Do you like to participate in it? It's like, okay. I really wasn't doing anything in quantum at the time, quantum education. But things have changed quite a bit since then. It's been quite exciting. Okay, so let me start with the usual about me stuff for those of you who aren't familiar with me or maybe don't know all of my dark secrets. First of all, I identify as a physicist, even though I do a lot of other stuff in my professional life. I am senior research scientist at UT. That's sort of my main research job. So I'm a staff member, not a faculty member for that. That's my main gig. And I also had the ARL UT Center for Quantum Research. So it's like a small little group of people who do quantum stuff and a larger group of people who know nothing about quantum. I'm also principal investigator and research educator for the quantum computing stream for our FRI, Freshman Research Initiative. So this is the undergraduate course that I teach. Actually, I started teaching again this year that runs spring through fall, and it takes incoming students who know nothing about quantum, and we go from everything from what's a qubit to like stabilizer codes. It's a lot of fun, and I enjoy teaching again. I'm also faculty lead for a high school program. We had piloted a high school program several years ago. That's actually when Justin first contacted me. It was in that capacity. And that's now migrated to a dual enrollment program that's now offered across the state of Texas. And finally, until rather recently, I was also a student pilot. I'm now a private pilot and also a basic ground instructor. And I mention this in part because it's humbling. This is a picture of me in one of my cross-country solos, and I forced myself to smile to take the selfie, but actually I was panicking because I couldn't find the airport, which is surprisingly difficult to do in the air. But it was a humbling experience because I went, if you're an adult learner who's learning like a totally different, new, challenging skill, and you're being taught by a bunch of 20-somethings, it's a very different experience, You're used to being very competent in what you do. And maybe some of you feel the same way here, where you're very competent, you're in your own field, but now you're being thrown into this QIS stuff, and it seems like totally foreign. But that experience really changed my way of thinking about education too. Like the perspective of learning a vocational skill that is like mission critical versus like a BS college course where the outcomes don't really matter. Like you really worry about what grade you give, how you evaluate people, what skills you really want them to have coming out. So I think about that a lot. Okay. So I'm going to talk to you today about Virtual Quantum Optics Laboratory. Some of you are familiar with this, some of you may not be. This is something that we developed back in 2019, and it was like a summer student project that I had in mind, and it was sort of fortuitous because my original idea was to have this as a supplement for our existing summer optics program. But it turned out pandemic came along and we're able to use this as an alternative for in-person optical experiments. and it actually turned out to be very successful. So I use this as both an educational tool, and I also use it as a research tool. And so you can find papers where I have little pictures of VQOL, like in as a physical review paper. I like to think of it as a graphical sandbox. It's not canned experiments. It's kind of like if you guys saw the fly trap thing that was presented yesterday, similar to that. It's got sort of all your basic linear optic components. It has some basic sources of light, lasers, entanglement sources, and so forth. And then kind of an odd twist is under the hood. Technically, it's a local hidden variable model, so we model everything as stochastic processes with deterministic detection events. So we treat basically the vacuum as though we're a real thing, and then model that as a random variable, and then detections are based on these amplitude thresholds. This discussion is going to be very interactive. If you have a laptop, it will be very helpful if you can pull it up and pull up the VQOL website. We're going to be doing a few exercises. If you don't have it ready just yet, that's fine. I'm going to kind of go through some of the capabilities of VQOL, and then we'll dive into a particular example. This is one of the canned examples that you can find in VQOL. It's Malice's law. This is one of the basics for understanding polarization. It's entirely classical here, of course. And what you see, there are a couple of things. First of all, there's a big optics table. That's where you put all of your stuff. There's a list of components that's over here on the left-hand side. You can select those, kind of click on them, drag and drop. You can do this on a phone or an iPad, but the interface is a little bit awkward. It's something I want to work on, having it more iPad and phone friendly. And then once you set things up, you press the run button and it runs your experiment. So in this case, we have an example with, we have polarization. There's a polarization key. One of the things I struggled with in first developing VQOL was how to represent polarization, because I know I wanted this to figure very prominently in the simulation, but there's no good way of doing this. You know, if it's horizontal or vertical, you can kind of look at it from the top down as little arrows or little dots. But once you get into more exotic forms of polarization, all that sort of goes out the window. I made the choice, which is not a great choice, but it's the best thing I could think of, to represent polarization in terms of colors. Of course, we all know why that's a bad idea, because in physics, the color of light is determined by the frequency or polarization, not the wavelength, but I don't think it's caused too much confusion. So there's a little key on this that tells you like what the different colors represent. And it also will include any arbitrary elliptical polarization. So I've shown kind of the basic 6, but if it's something in between, then it'll interpolate the colors in between there. So you'll see these like weird little Skittles rainbow things showing up, and this is just arbitrary elliptical polarizations. The different components, if you click on them, there's a little menu that allows you to configure them. You can put them in different places. You can orient them differently. And then they'll usually have some kind of setting, like for the polarization, or sorry, this is for the laser. You can set what sort of polarization the light comes out as and what the power level is. Similarly, polarizers, you can define them in terms of the angle for just linear polarization, and there's also a phase component that you can use to develop circular or elliptical polarizers. Halfway plates, these are used for rotating, so they act like unitary gates, and you can configure those in terms of fast axis angle. And then here's an example of the Born rule. So what I showed before was just kind of classical optics and power meters to read the raw power. That's not quantum, of course. And if you reduce the intensity of the light down low enough, then those power meters are just going to read 0. They're not going to be able to see anything. And then you get down into the quantum regime. So one way to do that is by placing a neutral density filter in front of your laser beam. Neutral density filter, if any of you guys are into photography, you might have seen these. It's just kind of a little smoky piece of glass that you put in front of your laser, and all it does is attenuate light. So it doesn't change the polarization, it's defined in terms of an optical density, which is power of 10, that it reduces the power or intensity of the light. So in this particular example, we have a laser that's putting out horizontally polarized light because it's red, and then we have a half-wave plate with a fast axis angle of 22.5 degrees, and that converts the light to diagonally polarized, which is indicated by yellow, and then that light goes through this neutral density filter, which then strips out the sort of reduces the classical component, but keeps the vacuum component in there. So now the kind of signal to noise ratio is more on par with unity, and you see a lot more randomness. So if I were to model this quantum mechanically, I would describe this as a separable state of two coherent states, alpha H and alpha V representing the amplitude and phase of the horizontal and vertical components of light. But the way that we do it internally is in terms of a random variable, which is a random or stochastic Jones vector representing the amplitude and of the two components, and then added to that is this vacuum component that has a scale factor of 1 over square root 2. The 1 over square root 2 represents the 1/2 h bar omega kind of ground state or vacuum energy. And then Z is are just complex numbers, IID standard complex Gaussians. Now, the light separates through a polarizing beam splitter, which ideally would transmit horizontally polarized light and reflect vertically polarized light. And then these detectors, the way that they operate is that they look at the instantaneous amplitude of the light incident upon them, both the horizontal and vertical components, and if either one falls above a threshold, then we say that we have a click. If that doesn't happen, it doesn't click. And so there's not an intrinsic notion of a photon in here. It's just stochastic light that is randomly generating these clicks. But this has many of the effects of a standard photonic system. So one of the things I was trying to do with VQOL here is, unlike, say, quantum flytrap, I didn't want to have an idealized model of quantum phenomena. I was doing this originally to complement an optics lab, and I wanted something that encompassed some of the realistic effects of real optical systems. And so detection is kind of an integral part of that. You don't really have ideal detectors. You don't have ideal photons. You have dark counts and you have misdetections or efficiencies. So that threshold then directly translates into a probability of a dark count or a dark count rate, which is something you can set on your detector. So you can change that threshold. If you make it lower, you'll detect more things. If you make it higher, you'll get fewer dark counts. But it's a bit of a trade-off. There's not an idealization. The individual segments, by the way, you see how the lines are kind of broken up into little chits. Those would represent the coherence length or coherence time of the light, the duration of time over which the polarization can be considered to be constant. For you electrical engineers, this is like a Rayleigh fading model where you assume the channel is constant for coherence time and then it changes to something else. Okay. All right. Now, since this is an approximation, one could look at what the correspondence is with like the standard Born rule. And so for the setup that we have there, where we've got coherent light and it's attenuated, and we're doing counts, we can look at the relative number of counts. In this case, we did it for optical density of 10 and probability of a dark count 0.1, which are the default settings in VQOL. And relative to like the cosine squared fit that you would expect for a Born rule, it's okay, pretty good. And that's assuming that we're translating counts into probability by looking at min-max counts and normalizing by that. One of the interesting things about experiment, and something that I think is important for students, is to make that connection between the things you actually measure and the things that are predicted in theory. So theory predicts probabilities, experiment observes counts, and how you make that connection between the two is extremely important. And it's also not always clear what that connection should be. So I chose one might choose others. If you increase the intensity and increase the threshold, you get better agreement, and then going further, you can get kind of arbitrarily good agreement. But it's going to be with a slower number of counts. Okay, so this gives you a kind of poor man's single photon source, where if you have high attenuation and you have high thresholds, it looks like it's a single photon that's spitting out, but it's not really. Entanglement, of course, is an important aspect of quantum and quantum optics. And the way that we model that is, again, using random variables. So in the device, the entanglement source kind of looks like this. It's, I don't know, it looks to me sort of like an oil filter on a car. I probably need to find a better symbol for it. And this can model a Bell state, but it's an approximation of a Bell state. So an ideal Bell state would look something like this, where you have superposition of horizontal for two photons coming out, and vertical, maybe there's a relative phase between them, and then a normalization. Experimentally, we don't actually generate these things. What we generate are what some people refer to as macroscopic Bell states. They're squeezed multimodal Gaussian states, so they include vacuum states and a Bell state with some scale factor, and then lots of other multi-photon states. You can represent this in the Heisenberg picture in terms of operators, and then translate that directly into random variables, which is what we do in our model. And so now those four different modes, the two different beams and then the two orthogonal polarizations, are modeled in terms of a linear combination of the four different vacuum modes that would contribute to it. But there's correlations between them, so that for one mode, it's dependent upon the vacuum state of a different mode. And that mismatch then leads to special correlations. So the result is that you have a vector which is a Gaussian random vector, but it's an improper Gaussian random vector, which is not something we normally encounter. Maybe the electrical engineers have heard of this, where you have a covariance matrix, but then you also have a pseudo-covariance matrix that's non-zero. And that turns out to be important for entanglement. So that's how things are modeled under the hood. Yes.
Dumb question. So you were saying that this behaves as if you were seeing individual photons.
Yes.
If we were to do this with real equipment in a real lab with the attenuation, would we actually be counting real photons?
You'll have to ask Tori about that. Okay. Just a nice little deflection there. Okay. So one of the things you can do is have the basic experiment is Bell's CHSH inequality, which is a famous experiment that's done to demonstrate quantum entanglement. So you have an entanglement source, you have two halfway plates, and then polarizing beam splitters and two sets of detectors. The halfway plates allow you to measure in different bases, and then the polarizing beam splitters allow you to differentiate horizontal and vertical. So it's like a measurement gate on KISS-KIT. And then the halfway plates, you can think of them as like just a unitary operation. For this particular case, we would be preparing a singlet state. So it's HV minus VH, which is a kind of Bell state. I happen to use a squeezing strength of 0.9. Squeezing strength is a representation of how bright the entangled light is. You don't want it too bright or it looks like classical light. You don't want it too low or it looks like just junk, or just vacuum. So something in between around unity is good. And then for the experiment, you can set the fast axis angles for Alice and Bob to be 4 different combinations of these 4 different settings. And what you do when you do a particular set of settings and you run the experiment, you then post-select on coincident counts, which is what you do experimentally. In VQOL, what you get out is this kind of long list of all the different combinations of detection events. So things where you just detected once on detector 1, things where you detected on detector 1 and detector 3, which would be considered a standard valid count. So like 1 and 3 would mean that you have horizontal here and then horizontal here. Well, that shouldn't happen according to this, but it does happen sometimes. So you have a small number there. But then 1 and 4, which is indicated here, that would be horizontal for Bob and then vertical for Alice. That has a pretty high number of counts, okay, which is consistent with it being a Bell state. And then from that, you can calculate a correlation where if they have horizontal and vertical, if they're the same, then it's +1. If they're different, it's -1. And you get a negative correlation, which is what you would expect for a Bell state. And then you do that for these 4 different combinations, put them together in this Bell statistic, and you get a number that's greater than 2. So this is possible because this is not an ideal experiment. These detectors do not have perfect efficiency, and that allows you to be able to violate this inequality. But it's similar to what you would do experimentally. Okay. We're going to jump into some exercises about the quantum eraser next, but I want to pause here for any questions or discussion. Yes, Olivera.
So we're building these quantum key distribution kits, and they're out of half-wave plates, and they're going to order them, and it's going to take 3 weeks, and it's going to be too late. And I guess we didn't order before because Janine gave us some, and I guess now we need more. So I've been Googling to see what they were. Is it like a prism sort of view, or is it like a film? Or what makes it change the phase?
That's a great question. I didn't get into any of the physics of how these things work. Halfway plate is a special kind of material. It's called a birefringent material. It's like a piece of glass or transparent material that has a different index of refraction for different polarizations. So there's a fast axis, which is where it just has a normal index of refraction, and then the opposite polarization direction, it's slowed down. And so what happens is when light goes through, the 2 components get out of phase with one another. And the halfway plate is designed so that, at least for certain wavelengths, by the time the light exits the glass, they're out of phase by half a wavelength. So if it's oriented like perfectly with the fast axis angle.
WP in your drawing there.
Yes.
And so that means that light going horizontally is going to be changed, phase will be changed by half a rotation or something, right?
Yeah, so what happens is that the vertically polarized, so if the fast axis angle is set to 0, then the vertically polarized light is slowed down, and the horizontally polarized component stays the same, and by the time it exits, they're half a wavelength out of sync.
Okay, and then the V's on the other one, those are the vertical plates. Yeah, V's.
These, no, that's just indicating what type of light goes through the polarizing beam splitter. So polarizing beam splitter is a device that's also birefringent, but it's designed so that horizontal light passes through it and the vertically polarized light gets reflected. And so having the detectors at those two outputs tells you what kind of light you should interpret that to be.
Yeah, so beam splitter is the second out of two components we're dealing with, and the issue there is that it's like $50 to buy one.
Right.
So I'm also wondering what it does. Okay, so it splits the beam, but you said in horizontal versus vertical?
Yes, yes.
90-degree angles, sort of.
Usually, depends on how they're made. $50 is pretty cheap for a polarizing beam splitter, so you should grab that. Also, probably not very good.
Oh, that's why the kids are not working. Okay, good.
Okay, I can move on to quantum eraser. Quantum eraser is an experiment that you guys will be doing later on with Tori in like a real lab, but I'm going to show you a simulated version of it to kind of get an idea of what it looks like and what's going on. The quantum eraser is kind of a variant of Wheeler's delayed choice experiment, which is a demonstration of the wave-particle nature of light. So it's a nice experiment to do. It's a fun thing to do in the lab, and it's not terribly difficult to do if you know what you're doing. Okay, so this is where, if you have VQOL set up, it would be great to set it up right now. What I'd like you to do is to just build this little experiment right here. And I'm going to go ahead and build it in vivo here so we can see how it's done. Let's see, I can do this. So when you log into VQOL, you can sign in under a Gmail account if you want to save your experiments, or you can just do it as a guest, which is what I'm going to do. We'll start off putting a laser on the table. Lasers are always good. I'm going to go ahead and set this one to 100 watts, which... Oh, is it not? No, you're right. Let's see. How do I do that? Okay. That's working now, right? Yes. Okay, great. Okay. So I place this laser. It's going to have horizontally polarized light. I've set it to 100 watts, which is not something I recommend you do at home unless you want to burn your equipment, but it makes it convenient for the experiment. And then we're going to place a regular or non-polarizing beam splitter. I'm going to leave 2 spaces there for other stuff later on. And so the beam splitter, if you go in step-by-step mode, you can kind of do this in slow motion. It takes the light and then it splits it into 2 components that are each half the intensity of the incoming beam. If you want to map that back to the stuff we talked about earlier, this acts like a Hadamard gate. I think Tom had mentioned that earlier. Beam splitters can be represented this way. So this is like taking a 0 state and then applying a Hadamard, and you get a plus state. Next, we're going to add in a mirror.
And is 0 and 1 here just vertical and horizontal?
Yes, yes. So 0 is horizontal, vertical is 1. And then a diagonal would be plus. I'll put a mirror here, and then as it is, it would just rotate flat. So I'm going to press the R button to rotate it. You can also change the orientation over here so that it now reflects it this way. And then I'm going to add another mirror over here and another beam splitter. The great thing about VQOL, I don't have to pay for all of the components, and they never go dead. Working in a student lab, the cost of losing a component is a real thing. Okay, so putting these all together now, we have what's called a Mach-Zehnder interferometer. If you think of this as a quantum circuit, this is like a Hadamard and then another Hadamard, right? And so we think about what happens here. We've got the beam splitter splits the light, of course, into two. The mirrors serve to just redirect the light so that they go back into the other one. And then the question is, what should happen when it re-enters the light? Well, these beam splitters act as unitary gates. They are reversible operations, conserve energy, all that good stuff. So we would expect that they act in the same way as if you took the light and you just reversed the direction of what was coming in, right? Think about what's coming into the beam splitter. It should act the same as what would come out of the beam splitter. To measure what happens, we're going to go ahead and put some power meters here. These are classical devices that allow you to just measure the intensity of the light, the power of the light coming in. And what does your intuition say should happen after the light enters that that second beam splitter? This will depend very much on whether you conceive of light as a particle or a wave. If you think of light as a particle, composed of photons, then it should be like a little Plinko machine. And the first one, it decides whether to go straight or turn, and then it goes along one of those two arms, and then it makes a decision of whether to go straight or turn again. That's how a particle would behave. It's not how a wave would behave. A wave would add constructively or destructively. All right, so it would add coherently. Yes?
How did you make those red lines? Most of us could not figure that out.
Did you press the run button up at the top here?
We are not even playing it. Should we play it?
Yes.
Now we should pause.
I'm just pausing for dramatic effect. Okay, so hopefully you guys are at the point where you can do this. Okay, so run the experiment forward. You'll find that what happens, and maybe this is surprising, maybe it's not. All of the light comes out from one direction, and you get the full 100 watts. And then the other one, you get just these little rainbow skittles, which is the vacuum state that's visualized here. There's a vacuum state on the other one, you just don't see it. So that's the constructive interference, that's the wave-like behavior of light. So this is classical light, it's behaving in a classical manner, we would expect that, okay? Now, we're going to modify the experiment by adding in a new component. We're going to add in a halfway plate, which, as you recall, rotates the polarization. Rotates it in kind of an odd way. So we're going to rotate it to get vertical polarization. To do that, we have to set the fast axis angle to 45 degrees. It takes horizontal light and rotates it by twice the fast axis angle. And so now what happens, don't want to give away the farm. When it exits the halfway plate, that light now turns blue, and blue, according to our polarization key, corresponds to vertically polarized light. So we've changed the polarization. What this allows us to do is to kind of put a little marker on the light. So if you imagine this as a photon, then that means that depending upon which way it chose to go out of that first beam splitter, it would get marked as either horizontal or vertical. It would be like painted blue or red. And so you should be able to detect that on the opposite end, and then you find out once and for all which way it went. Okay. And so when they combine together, then what happens? Is anyone having trouble setting this up or getting these experiments running? You guys are good? Yes? If you hit reset, maybe.
I don't have a reset. Let's see if I can. Oh, now I see it. Oh, now I see the reset. Oh, okay.
Okay. You can also press stop, and it'll just run the experiment to completion, and then you can start it over again.
That didn't happen for me.
Okay.
I pressed stop, it said stopping,
Yeah.
and then I wish, and stopping, and stopping, and stopping.
It should, so there's a little time left thing over here, and it's set for like 1 millisecond of lab time, so it'll just count down to that, and then it'll stop.
I don't have the blue light coming out of the halfway.
Okay. Are you sure that you have a halfway plate? So if you highlight it, it should say halfway plate, and then you should have the angle set to 45. Mm-hmm.
But I have Skittles all the way. I don't get the green, the red lines. Was I supposed to set the light source or something?
Okay. You should have your laser set to 100. You're getting blue and red. And then, okay, I'm going to go around in a moment, but I'd like to move forward here. Okay, so what happens is that these two are going to add coherently. This is like taking the two components of like a 0 and a 1 state. So this would be like a plus state going into a Hadamard. And then what comes out, we have two components here. It's coming out as a diagonal, so it's a linear combination of those two things, and there's a phase difference between them because of the unitarity, but it's coming out diagonal. Okay. So yeah, these are in the diagonal. These are actual diagonal polarizations. The yellow is diagonal. The green is anti-diagonal, and they each have a power of 50 watts, so it's half the power. So it's split evenly between the two. And that's kind of like the sort of thing you would expect with a particle-like behavior where you would get equal amounts of stuff on either end, right? So this is like the particle-like behavior. This is all classical light. Okay. The quantum eraser is about how you can remotely change that or recover that interference pattern. So what you're erasing is the which way information about what path it goes in. And here's a very kind of poor man's way of doing this. What you can do is you can add another component, which is a polarizer. And a polarizer, you guys are familiar with like polarizing sunglasses. There's a bunch of them over in the library there. And so they take out one component of the light, and in this case I'm going to set it to be 45 degrees, so that means that the polarizer, it's a linear polarizer in this case, and it's going to transmit out the component of the light that is diagonal. So when it comes out as diagonally polarized. It's also reduced by 1/2 the power, but that's okay. And then everything else kind of works as before, except now when that diagonally polarized light goes into that halfway plate, this is like a plus state going into a Hadamard. I'm sorry, not a Hadamard, going into a NOT gate. If you had a plus state going into a NOT gate, what would that result in? It would be another plus state, right? Just switches 0 and 1. So it comes out, again, as diagonally polarized. That's sort of the erasing part. So now the two paths have the same polarization. And now as we run through the rest of the experiment, we find that we recover this wave-like behavior where now both paths have the same polarization and they add together constructively. Okay, but we did that remotely. We did that over here. We didn't change anything over here. Okay, so this was all with classical light. And what we're going to do next is look at how to do this with quantum light.
What was the angle on the polarizer?
Polarizer is 45 degrees. this is a little confusing because the polarizer is 45 degrees, which means that the light comes out 45-degree angle. The halfway plate, the angle is for the fast axis angle, and that's just a parameter of how you rotate the plate, which doesn't necessarily correspond to the polarization of the light coming out. And the halfway plate was also set to 45 degrees, but that actually rotates the horizontal by 90 degrees, so it gives you vertical, but it takes the diagonally polarized light and doesn't do anything to it. You're basically putting the fast axis angle already at the diagonal, so it's acting like nothing's happening. Okay. So to go further now into the quantum realm, we're going to introduce a neutral density filter. So we saw those earlier, and that's this little component right here. And I'm going to put this right here in between the first beam splitter and the polarizer. And I'm going to go ahead, since we're using a really high-powered laser here, I'm going to up the optical density to 14. So that reduces the power by 10 to the 14th power, 14 decades. Okay, so we're down into the quantum realm here. And when we do that, what we'll see is that it's a bunch of Skittles rainbows, and the power is 0 on each of these guys. We're now too low for the power meters to work. We're not in the classical regime anymore, and so to say bye-bye to our power meters and hello to our detectors. So the detectors look like this, and I'm going to press the R button to rotate it so that the business end is facing towards the light. I'll put in another one over here, and for the detectors, it's very important that the optical path length to each detector be the same. So I spaced each of these one segment away from the second beam splitter, and that's so that they're detecting at the same time, and I can look at coincident counts and such. Okay, so now we just did this in the classical regime, and now we can do this in the quantum regime, and the question is, what's going to happen? Well, if I just run the experiment, first of all, I'm not going to see anything obvious just by looking at it. It's all these little Skittles rainbows, so we're very close to the vacuum state. And what I'm going to have to do instead is to look at counts. And what I'll find is that, well, a lot of the time I don't detect anything. I'm just waiting and waiting and waiting for something to happen. And then every now and then, boop, I get a detection. I get a detection on one, and then I keep going, boop, another one. Right? And it looks very particle-like, right? Seeing individual things and they're clicking. And so this looks like you're getting individual photons clicking. All right. And if I just run the whole experiment, what's going to happen is that at the end of the experiment, it's going to summarize the results. In this case, we only have 2 detectors, so it summarizes it very simply. It says detector 1, we got 94 counts. Detector 2 only, I get 7 counts. And then there are oddly 3 counts where I got a detection on both 1 and 2. So these are double detections. In the laboratory, you would say this was a double photon event. This is not an ideal single photon source. It's a weak coherent light, which means it's a superposition of vacuum state, which we saw a lot of. There are just no detections, single photon states, and then 2 photon, 3 photon, etc., out in a Poissonian distribution. So occasionally you do get 2 detections. That's a real thing, and that's reflected here. But most of the time you're getting a single detection, and that corresponds to what we saw classically as having all of the light intensity on that one output beam. Yes, Wayne?
Here means within a really small period of time.
In this case, we...
Kind of the same time.
Oh, yeah, so these things are kind of lockstep in little microsecond time steps. So when I say that detector 1 and detector 2 clicked at the same time, I have a coincidence window that is that microsecond. In real experiments, you can get timing down to, say, about a nanosecond, and you have a flexibility as to what you want to consider that coincidence window. Microsecond of coincidence is not unreasonable, but that's what we have set up here. So yeah. Yes, George.
Do you account for noise?
Implicitly. So the noise is treated entirely through the vacuum. So the vacuum is random. All randomness comes from the vacuum. There's no other source of noise.
Is it Gaussian?
Yes. And so it follows the Gaussian distribution of the vacuum state as represented in quantum optics. Okay. Y'all good with that? We're doing all right? Okay, I think we're doing pretty good on time, actually. What I want you to do, we're going to do one experiment here up until the top of the hour. And what I want you to do is just try out different combinations where I want you to go take this polarizer out, try to get back to that wave-particle duality where you can change this half-wave plate, make it 0, make it 45, wave-particle, and then quantum eraser, you put that thing back in. So we're going to kind of go through those same steps we had before, try those different combinations. Okay? We'll do that, give you guys 10 minutes to play around, and I'll go around and answer any questions. And then we'll go on to the entanglement version of this.